Hello there, and welcome to the Sleepy Library. Tonight, we are drifting into the deepest mysteries of the universe, where gravity becomes so strong that even light cannot escape. We are entering the world of black holes, strange and powerful places in space that bend time, shape galaxies, and push the limits of physics. Black holes are not just empty darkness. They are incredibly dense objects that pull in everything around them, creating regions from which nothing can return. Time moves differently there, and space twists in ways that are hard to imagine. This journey is not only about space, but also about wonder. Everything we explore tonight comes from real science, careful observation, and the curiosity of people trying to understand the universe. If you enjoy these quiet journeys, feel free to like, subscribe, or share a thought below. It helps others find their way here, one sleepy soul at a time. For now, take a slow breath. Let the night settle around you. Let's begin. Black holes are not empty. Though their name suggests a void, black holes are among the most massive and dense objects in existence. They pack immense amounts of matter into impossibly small regions of space. The mass that once belonged to stars, sometimes millions or even billions of times more massive than our Sun, gets compressed into a point so tiny it has no measurable size. This concentration of mass creates gravitational fields so intense that they alter the shape of space itself, bending it inward, like a deep well from which nothing can climb back out. The closer you approach one of these objects, the more dramatically space curves, time slows, and the familiar rules of motion begin to change. Black holes are not emptiness. They are density beyond comprehension, gravity made visible through its effects on everything around it. They are the universe's most extreme compression chambers, where matter has been crushed beyond all atomic structure, beyond all familiar form, into something that exists only as pure gravitational influence, pure warping of reality. The event horizon is the point of no return. Surrounding every black hole is an invisible boundary known as the event horizon, a spherical surface that marks the threshold beyond which escape becomes impossible. It is not a physical barrier, not a wall or a membrane, but rather a mathematical boundary defined by gravity. At the event horizon, the escape velocity, the speed needed to break free from the gravitational pull, equals the speed of light. Since nothing in the universe can travel faster than light, anything that crosses this boundary is forever trapped. For an observer watching from a safe distance, an object approaching the event horizon would appear to slow down, its light redshifting into dimmer and dimmer wavelengths as time itself stretches near the boundary. The object would seem to freeze at the edge, never quite reaching it, fading gradually into darkness. But from the perspective of the object itself, it would cross the horizon in finite time, experiencing nothing unusual at that precise moment. The event horizon is a one-way door through which matter, energy, and information can enter but never leave, a threshold that divides the universe into two regions, the knowable and the forever hidden. Black holes come in different sizes. Astronomers classify black holes into several categories based on their mass, each with its own origin story and characteristics. Stellar mass black holes, the most common type, form when massive stars exhaust their fuel and collapse under their own gravity. They typically range from about 3 to 50 times the mass of our Sun, compressed into a sphere only a few kilometers across. Then there are supermassive black holes, monsters that lurk at the centers of most large galaxies, including our own Milky Way. These behemoths can weigh millions to billions of times the mass of the Sun, their event horizons stretching across distances larger than our entire solar system. Between these two extremes lie intermediate mass black holes, ranging from hundreds to thousands of solar masses. These are harder to find and may form through the merger of smaller black holes in dense star clusters. Finally, there are theoretical primordial black holes, hypothesized to have formed in the first fractions of a second after the Big Bang, when quantum fluctuations in the early universe created regions dense enough to collapse directly into black holes. These could range from microscopic sizes to thousands of solar masses and, if they exist, may help explain some of the universe's deepest mysteries, including the nature of dark matter. Stellar mass black holes form from dying stars. When a star at least 20 times the mass of the Sun reaches the end of its life, it faces a spectacular fate. Having burned through its nuclear fuel, the star can no longer generate the outward pressure needed to counteract its own gravitational pull. The core collapses catastrophically, rebounding in a supernova explosion that can briefly outshine an entire galaxy. But while the outer layers of the star are flung into space, enriching the cosmos with heavy elements forged in the stellar furnace, the core continues to collapse. If the core's mass exceeds about 3 solar masses, not even the quantum pressure of neutrons can halt the inward crush. The core collapses past the point where it could form a neutron star, shrinking without limit, compressing matter beyond all atomic and nuclear structure until it forms a black hole. This process happens quickly, in mere seconds, but the black hole that results will exist for timescales that dwarf the current age of the universe. These stellar remnants, born in violence, become silent dark points in space, detectable only by their gravitational influence on nearby matter or by the radiation emitted from material falling into them. Supermassive black holes live at the centers of galaxies. Almost every large galaxy in the universe harbors a supermassive black hole at its core, a cosmic anchor around which millions or billions of stars orbit. Our own Milky Way galaxy contains one called Sagittarius A star, which has a mass equivalent to about 4 million suns. Despite its enormous mass, its event horizon is only about 17 times the diameter of our Sun, a remarkably small region given the gravitational dominance it exerts over the entire galactic center. These supermassive black holes did not form from the collapse of single stars. Instead, they likely grew over billions of years through a combination of mergers with other black holes and the steady accretion of gas, dust, and stars from their surroundings. Some may have started as smaller seed black holes that formed early in the universe's history and grew rapidly by feeding on the dense gas clouds available in young galaxies. Others may have formed directly from the collapse of massive gas clouds in the early universe. The relationship between supermassive black holes and their host galaxies is intimate. The mass of the central black hole is closely correlated with the properties of the galactic bulge, suggesting that black holes and galaxies evolve together, influencing each other's growth and structure over cosmic time. Black holes are not cosmic vacuum cleaners. Despite their fearsome reputation, black holes do not roam through space sucking up everything in their path. Their gravitational influence extends only as far as any object of similar mass would exert. If our Sun was suddenly replaced by a black hole of equal mass, Earth would continue in its orbit unchanged, experiencing the same gravitational pull as before, only colder and darker without sunlight. Black holes capture matter only when that matter ventures too close, crossing into the region where the gravitational pull becomes inescapable. Far from a black hole, space is relatively normal. Stars can orbit safely around supermassive black holes for billions of years, just as planets orbit stars. It is only when objects stray too close, through chance encounters or gradual orbital decay, that they face the black hole's full power. Even then, not all material falls directly in. Much of it swirls into an accretion disk, a flattened, spinning structure where friction and magnetic forces heat the material to millions of degrees, causing it to glow brightly in X-rays, before eventually spiraling inward past the event horizon. The singularity lies at the heart. At the very center of a black hole, according to general relativity, lies the singularity, a point where all the black hole's mass is concentrated into zero volume, creating infinite density and infinite curvature of space-time. It is here that our current understanding of physics breaks down completely. General relativity predicts the singularity, but cannot describe what happens there because the equations produce infinities that have no physical meaning. Similarly, quantum mechanics, which governs the behavior of particles at the smallest scales, fails to account for the extreme gravitational conditions near the singularity. The true nature of what exists at a black hole's core remains one of the greatest unsolved problems in physics, a place where the two pillars of modern physics, general relativity and quantum mechanics, come into direct conflict. Some physicists speculate that at the singularity, space and time themselves may break down into something more fundamental, perhaps a quantum foam of fluctuating geometry. Others suggest that the singularity might be avoided entirely in a complete theory of quantum gravity, replaced by something finite and describable. For now, the singularity remains hidden behind the event horizon, forever inaccessible to observation, a mathematical ghost in the equations of Einstein's theory. Time slows down near a black hole. One of the most mind-bending consequences of a black hole's intense gravity is the phenomenon known as time dilation. According to Einstein's theory of general relativity, gravity warps not only space, but also time. The stronger the gravitational field, the slower time passes relative to a region of weaker gravity. Near a black hole's event horizon, this effect becomes extreme. An astronaut falling toward a black hole while being observed by someone far away would appear to move slower and slower as they approached the horizon. Their watch would tick at an ever-decreasing rate. Light from their spacesuit would redshift toward longer, dimmer wavelengths, and they would seem to freeze in time at the edge, never quite crossing over. But from the astronaut's perspective, time would feel perfectly normal. They would cross the event horizon in a finite amount of their own time, unaware of the vast stretches of external time passing outside. This warping of time means that near a supermassive black hole, one could theoretically experience only minutes, while hours, days, or even years pass in the wider universe, a form of time travel into the future, though with no possibility of return. Spaghettification stretches matter into strands. As an object approaches a black hole, it experiences tidal forces, the difference in gravitational pull between the parts of the object closest to the black hole and those farthest away. For small black holes, these tidal forces become extreme even before the event horizon is reached. If you were falling feet first into a stellar mass black hole, The gravitational pull on your feet would be vastly stronger than on your head, stretching your body longer and longer, while simultaneously compressing you from the sides. This process, whimsically named spaghettification, would eventually tear you apart at the molecular level, reducing you to a thin stream of atoms spiraling toward the singularity. The point at which spaghettification becomes fatal depends on the black hole's mass. For stellar mass black holes, the tidal forces are lethal well outside the event horizon. But for supermassive black holes, the event horizon is so large, and the curvature of space so gradual at that boundary, that you could cross it without feeling anything unusual. The spaghettification would occur later, much closer to the singularity deep inside the black hole. This difference is due to the fact that tidal forces depend not just on the strength of gravity, but on how rapidly gravity changes over distance, and this gradient is much gentler for massive black holes. Black holes emit Hawking radiation. In 1974, physicist Stephen Hawking discovered that black holes are not entirely black. Through a quantum mechanical process occurring just outside the event horizon, black holes can emit radiation and, over unimaginably long timescales, slowly evaporate. The radiation arises from the quantum vacuum, which constantly produces virtual particle-antiparticle pairs that normally annihilate each other almost instantly. Near the event horizon, however, one particle from a pair can fall into the black hole, while the other escapes as real radiation. From a distant observer's perspective, the black hole appears to be radiating particles. This radiation carries energy away from the black hole, causing it to lose mass over time. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A stellar mass black hole radiates at a temperature of only a few billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation, so it actually gains more energy from its surroundings than it loses through Hawking radiation. But smaller black holes would radiate more intensely. A black hole with the mass of a mountain would glow hot enough to be visible, and one with the mass of a large asteroid would explode in a burst of gamma rays as it evaporated completely. Supermassive black holes radiate at temperatures so low they will take trillions upon trillions of years to evaporate, far longer than the current age of the universe. The first image of a black hole was captured in 2019. For decades, black holes existed only in mathematical equations and indirect observations. But in April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. The image showed the supermassive black hole at the center of the galaxy, Messier 87, located 55 million light-years from Earth. The black hole's mass was estimated at 6.5 billion times that of the Sun, and the image revealed a dark circular region, the shadow of the event horizon, surrounded by a bright ring of glowing gas heated to billions of degrees as it swirled toward the black hole. The shadow appeared larger than the event horizon itself because the black hole's gravity bent light from behind it, creating a dark region about 2.5 times the size of the actual horizon. This image was not produced by a single telescope, but by a global network of radio observatories working in concert, creating a virtual telescope the size of Earth itself. The achievement required synchronizing atomic clocks at observatories on multiple continents, recording petabytes of data, and performing complex analysis to construct the image from radio wave observations. It was visual confirmation of what Einstein's equations had predicted over a century earlier, a direct glimpse of one of the universe's most extreme objects. Black holes can merge and create gravitational waves. When two black holes orbit each other, they emit gravitational waves, ripples in the fabric of space-time itself that travel outward at the speed of light. As the black holes spiral closer together, they lose energy to these waves, causing their orbit to shrink and accelerate. In the final moments before they merge, the black holes whip around each other hundreds of times per second, releasing more power in gravitational waves than all the stars in the observable universe emit in light. When they finally collide and merge into a single larger black hole, the gravitational wave signal reaches a peak before abruptly cutting off as the merged black hole settles into a stable state. The first direct detection of gravitational waves came in September 2015, when the LIGO observatories detected the merger of two black holes about 30 and 29 times the mass of the Sun, located over 1 billion light-years away. The merger created a final black hole of 62 solar masses, with 3 solar masses worth of energy radiated away as gravitational waves in a fraction of a second. This detection confirmed a major prediction of general relativity and opened a new way of observing the universe, one based not on light, but on the warping of space-time itself. Since then, dozens of black hole mergers have been detected, revealing a population of these objects more diverse and numerous than previously imagined. Some black holes spin at incredible speeds. Black holes can rotate, and many spin at a significant fraction of the maximum rate allowed by physics. The rotation is a consequence of the angular momentum of the matter that formed the black hole, inherited from the spinning star that collapsed or accumulated through the accretion of matter falling in at angles rather than straight down. A spinning black hole drags space-time around with it in a phenomenon called frame dragging. Near the event horizon of a rapidly rotating black hole, space itself is pulled along in the direction of rotation so strongly that nothing, not even light, can remain stationary. There is a region called the ergosphere, just outside the event horizon, where everything must move in the direction of the black hole's spin. The fastest spinning black holes rotate at velocities approaching the speed of light at their equators. These spins affect the shape of the black hole, causing it to bulge at the equator and flatten at the poles, much like how Earth bulges slightly due to its rotation, though far more dramatically. The spin also affects how energy can be extracted from the black hole through a process theorized by physicist Roger Penrose, where particles entering the ergosphere can split, with one falling into the black hole and the other escaping with more energy than it had initially, effectively stealing rotational energy from the black hole itself. Rogue black holes can be ejected from galaxies. When two black holes merge, they can receive a powerful kick from the asymmetric emission of gravitational waves, launching the newly formed black hole away at speeds of up to several thousand kilometers per second. If the kick is strong enough, the black hole can be ejected from its host galaxy entirely, becoming a rogue wanderer in intergalactic space. These ejected black holes would be extremely difficult to detect because they lack the surrounding gas and stars that typically make black holes visible. Without an accretion disk or companion star, a rogue black hole would be nearly invisible, betraying its presence only through gravitational lensing if it happens to pass in front of distant background stars, bending their light in detectable ways. Astronomers have identified a few candidate objects that may be such recoiling black holes based on observations of quasars with unusual properties or apparent motion relative to their host galaxies. The existence of these wanderers suggests that intergalactic space may be sparsely populated with invisible black holes drifting through the void, remnants of ancient mergers that sent them flying away from their galactic homes. Black holes can grow by eating stars. Occasionally, a star wanders too close to a supermassive black hole and is torn apart by tidal forces in an event known as a tidal disruption event. As the star is pulled apart, roughly half of its material falls back onto the black hole, forming a temporary accretion disk that glows brightly in X-rays and ultraviolet light. The flare can be detected from billions of light-years away as the black hole suddenly brightens, sometimes by factors of thousands or millions, before fading over months or years as the disrupted star's material is consumed. Observations of these events provide valuable information about the masses and spins of supermassive black holes and the properties of the stars they destroy. In rare cases, tidal disruption events have been observed off-center from galaxies, suggesting the presence of rogue supermassive black holes or binary black hole systems, where two supermassive black holes orbit each other, each occasionally capturing and devouring a passing star. These violent events are a reminder that the neighborhoods around supermassive black holes, though vast, are not safe. Stars passing within a certain distance, called the tidal disruption radius, will be shredded regardless of their composition or structure, their atoms scattered into glowing ribbons that briefly illuminate the black hole's dark reign. Some black holes have jets. Many black holes, particularly supermassive ones, launch powerful jets of plasma that shoot out from near the poles at close to the speed of light. These jets can extend for hundreds of thousands or even millions of light-years, far beyond the host galaxy, carving vast cavities in the intergalactic medium and heating surrounding gas to temperatures of millions of degrees. The jets are powered by the rotational energy of the black hole and the magnetic fields threading through the accretion disk. As matter spirals inward, magnetic field lines get twisted and amplified, creating enormous magnetic pressures that can accelerate charged particles to relativistic speeds and funnel them outward along the black hole's rotational axis. The exact mechanism by which jets are launched and collimated into narrow beams remains an active area of research, but observations show that they carry away tremendous amounts of energy and momentum, profoundly affecting galaxy evolution by regulating star formation and redistributing matter and energy on galactic scales. When one of these jets points nearly directly at Earth, the black hole system appears extraordinarily bright and is classified as a blazar. Blazars are among the most energetic and variable objects in the universe, flickering on timescales of days or hours as turbulence in the jet causes it to brighten and dim. Black holes can be detected through X-rays. While black holes themselves emit no light, the matter falling into them can become extraordinarily luminous. As gas spirals inward through an accretion disk, gravitational energy is converted into heat through friction and magnetic interactions. The inner regions of the accretion disk, closest to the event horizon, can reach temperatures of millions or even billions of degrees, hot enough to emit copious amounts of X-rays. These X-rays can be detected by space-based telescopes, revealing the presence of black holes, even when they cannot be seen directly. In binary star systems, where a black hole orbits a companion star, the black hole can pull gas away from the star, forming an accretion disk that glows brightly in X-rays. Many of the known stellar mass black holes in our galaxy were discovered this way, as X-ray sources that flicker and vary as blobs of hot gas spiral inward. The pattern of X-ray variability can reveal information about the black hole's mass, spin, and the structure of the accretion disk. Rapid flickers on millisecond timescales indicate gas orbiting very close to the event horizon, while longer-term variations may reflect instabilities in the disk or changes in the rate at which matter is being fed to the black hole. The nearest black hole is about 1,500 light-years away. For a long time, the closest known black hole to Earth was thought to be several thousand light-years distant, safely remote from any immediate concern. However, more recent discoveries have identified candidate black holes significantly closer. One system, containing a black hole about 10 times the mass of the Sun, lies roughly 1,500 light-years away in the constellation Ophiuchus. It is part of a binary system orbiting a companion star and was discovered through careful analysis of the star's motion as it is tugged by the black hole's gravity. Even at this relatively close distance, the black hole poses no threat to Earth. Its gravitational influence extends only as far as any star of similar mass would, and it is not massive enough to affect objects outside its immediate stellar neighborhood. The discovery of nearby black holes helps astronomers understand the population of these objects in our galaxy and provides opportunities to study them in greater detail than more distant examples. As observational techniques improve, it is likely that more black holes will be discovered in Earth's cosmic backyard, invisible companions to visible stars, quietly lurking in the darkness between more luminous neighbors. Black holes can exist in pairs. In many galaxies, particularly those that have undergone mergers, two supermassive black holes can orbit each other at the galactic center, forming a binary black hole system. As the galaxies merge, their central black holes sink toward the center of the combined system through a process called dynamical friction, where gravitational interactions with surrounding stars gradually rob the black holes of orbital energy, causing them to spiral inward. Eventually, if the black holes get close enough, they will begin to lose energy to gravitational waves and merge on much shorter timescales. These binary supermassive black holes are difficult to confirm observationally because the separations between them are often very small, requiring extremely high-resolution observations to resolve them individually. However, astronomers have identified several candidate systems based on unusual variability in quasar light, dual cores in galactic nuclei, and other indirect evidence. When binary supermassive black holes finally merge, they will produce gravitational wave signals far more powerful than those from stellar mass black hole mergers, though at lower frequencies that require different detection methods, such as pulsar timing arrays or future space-based gravitational wave observatories. These mergers are among the most energetic events in the universe, reshaping the central regions of galaxies and potentially ejecting stars and gas into the intergalactic medium through the gravitational wave recoil kick. Primordial black holes could explain dark matter. One of the greatest mysteries in cosmology is the nature of dark matter, the invisible substance that makes up about 85% of all matter in the universe. Dark matter does not emit, absorb, or reflect light, making it detectable only through its gravitational effects on visible matter, gas, and the structure of the cosmos. While most physicists believe dark matter consists of exotic subatomic particles that have yet to be discovered, an alternative hypothesis suggests that some or all of dark matter could be composed of primordial black holes. These would be black holes, formed not from stellar collapse, but from density fluctuations in the first fraction of a second after the Big Bang, when regions of higher density could have collapsed directly into black holes. If primordial black holes exist in the right mass range and sufficient numbers, they could account for the gravitational effects attributed to dark matter without requiring new physics beyond general relativity. However, observational constraints have ruled out primordial black holes as the sole explanation for dark matter over most mass ranges. They could still contribute a small fraction of the dark matter, and searches continue for evidence of their existence through gravitational microlensing, their effects on cosmic structure formation, or the possible detection of Hawking radiation from the smallest examples. Black holes distort the light around them. The intense gravity of a black hole bends the path of light passing near it, an effect called gravitational lensing. Light from stars or galaxies behind a black hole follows curved paths through the warped space-time, causing the background objects to appear distorted, magnified, or multiply-imaged. Close to the event horizon, the bending becomes so severe that light can orbit the black hole multiple times before either escaping to infinity or falling in. This creates a structure called the photon sphere, located about 1.5 times the event horizon radius for a non-spinning black hole, where photons can theoretically orbit in a circular path. Any light emitted slightly inside the photon sphere will spiral inward and be captured, while light emitted just outside can escape, but will be significantly redshifted and delayed. The photon sphere contributes to the appearance of the black hole's shadow, the dark region seen in the Event Horizon Telescope images. The shadow is actually larger than the event horizon, because it includes both the event horizon and the region where light is so strongly bent that it cannot escape. Gravitational lensing by black holes also allows astronomers to study background objects and the space-time structure around the black hole itself, testing general relativity in the strongest gravitational fields accessible to observation. Some black holes are billions of times the mass of the Sun. The most massive black holes known, found at the centers of the largest galaxies, can reach masses of tens of billions of solar masses. One of the most massive known examples is the black hole at the center of the galaxy, Holmberg 15A, estimated to weigh at least 40 billion times as much as the Sun. These ultramassive black holes likely grew through a combination of gas accretion and multiple mergers with other black holes over billions of years. Their event horizons are correspondingly enormous, large enough to encompass the orbits of several planets in our solar system. Despite their immense mass, the density within the event horizon, calculated by dividing the mass by the volume enclosed, can be surprisingly low for the largest examples, comparable to or even less than the density of air for the most massive ones. This is because the radius of the event horizon increases linearly with mass, while the volume increases with the cube of the radius, so larger black holes are less dense on average. These giants dominate the gravitational landscape of their host galaxies, influencing the motion of stars, gas, and even entire star clusters over distances of thousands of light-years from the galactic center. Black holes can power quasars. Quasars are among the most luminous and distant objects in the universe. single points of light that can outshine entire galaxies by factors of hundreds or thousands. They are powered by supermassive black holes, actively feeding on vast amounts of gas and dust. As this material spirals into the black hole through an accretion disk, the conversion of gravitational potential energy into heat and radiation produces the quasar's immense luminosity. A typical quasar can emit the energy equivalent of hundreds of suns consumed per year, with most of that energy radiating from a region smaller than our solar system. The quasar era occurred primarily in the early universe, between 1 and 3 billion years after the Big Bang, when galaxies contained abundant gas to fuel rapid black hole growth. Today, most supermassive black holes are far less active, having exhausted or driven away the easily accessible gas in their vicinity. Our own galaxy's central black hole, Sagittarius A star, is currently dormant, accreting only small amounts of matter and emitting relatively little radiation compared to its potential if fed more vigorously. Quasars provide astronomers with a way to study black holes and galaxy evolution at early cosmic times, offering glimpses into an era when the universe was younger and more turbulent, and when black holes grew rapidly to their current enormous sizes. Binary black holes produce chirp signals. When two black holes orbit each other and spiral inward, the gravitational waves they emit increase in frequency and amplitude, creating a characteristic signal known as a chirp. In the final moments before merger, as the black holes accelerate around each other hundreds of times per second, the gravitational wave frequency sweeps upward rapidly, much like the rising pitch of a chirping bird, hence the name. The chirp signal encodes information about the masses and spins of the merging black holes, their distance from Earth, and the properties of their final moments together. By analyzing these signals, astronomers can reconstruct the event in detail, determining not only the properties of the individual black holes, but also testing general relativity in regimes of extreme gravity and velocity where it had never been tested before. The detection of gravitational wave chirps from dozens of black hole mergers has confirmed that these events are relatively common in the universe, occurring perhaps once every few minutes somewhere in the observable cosmos, most too distant to detect with current instruments. Future gravitational wave detectors, more sensitive and covering different frequency ranges, will allow astronomers to detect mergers throughout cosmic history, mapping the population of black holes across the age of the universe, and tracing the history of galaxy mergers and structure formation through the signature of colliding black holes. Black holes are quieter than you might think. While the regions immediately around black holes, especially the accretion disks and jets, can be scenes of incredible violence and energy release, the black hole itself is remarkably simple and featureless. According to the no-hair theorem in general relativity, a black hole is completely characterized by just three properties: its mass, its electric charge, and its angular momentum or spin. All other information about the matter that formed the black hole, its composition, structure, history, is lost once it crosses the event horizon. Two black holes with the same mass, charge, and spin are indistinguishable from each other, regardless of whether they formed from collapsing stars, merged from smaller black holes, or condensed from primordial fluctuations. This simplicity stands in stark contrast to the complexity of stars, planets, or any other astronomical object, which have rich internal structures, chemical compositions, and detailed surfaces. A black hole is, in a sense, the ultimate minimalist object, defined entirely by a few numbers and a curved region of space-time. This simplicity is part of what makes them so tractable, mathematically and paradoxically so mysterious, because it raises deep questions about what happens to information that falls into a black hole and whether it is truly lost or somehow preserved in ways we do not yet understand. The black hole information paradox puzzles physicists. When matter falls into a black hole, it appears to carry information with it about its properties, structure, and quantum state. But according to classical general relativity, this information is lost forever behind the event horizon, inaccessible to external observers. This conflicts with quantum mechanics, which holds that information cannot be destroyed, only transformed or redistributed. The conflict between these two fundamental principles leads to what is known as the black hole information paradox. Stephen Hawking initially argued that information is indeed lost, but in his later years, he revised his position, suggesting that information might be preserved in subtle correlations in the Hawking radiation emitted by the black hole. However, exactly how this works remains unclear and is a subject of intense debate among theoretical physicists. Some propose that information is encoded on the event horizon itself in a holographic manner where the two-dimensional surface contains all the information about the three-dimensional interior. Others suggest that firewalls might exist at the event horizon, incinerating anything that crosses, though this contradicts the smooth passage predicted by classical general relativity. Resolving the information paradox likely requires a complete theory of quantum gravity, a unified framework that consistently describes gravity at the quantum level, which remains one of the great unsolved problems in theoretical physics. Until such a theory is developed, the fate of information in black holes will remain one of the deepest mysteries at the intersection of quantum mechanics and gravity. The universe could be full of tiny black holes. If primordial black holes formed in the early universe, they could span an enormous range of masses, from far smaller than an atomic nucleus to thousands of times the mass of the Sun. The smallest of these, sometimes called micro-black holes, would be incredibly tiny, with event horizons smaller than subatomic particles. According to Hawking's calculations, such tiny black holes would evaporate almost instantaneously through Hawking radiation, exploding in bursts of high-energy particles and gamma rays. Micro-black holes with masses less than a few 100,000 kilograms would have evaporated long ago, within the first fraction of a second after the Big Bang. However, slightly more massive primordial black holes, with masses comparable to large asteroids or moons, could still exist today, slowly evaporating over timescales longer than the current age of the universe. Searches for these objects have been conducted using various methods, including looking for the gamma-ray bursts expected from evaporating black holes and searching for gravitational lensing effects as they pass in front of distant stars. So far, no definitive evidence for primordial black holes has been found, but the possibility remains open within certain mass ranges, and the search continues. If they exist, these ancient relics from the universe's first moments would provide invaluable insights into the conditions that prevailed in the earliest epochs of cosmic history, when the universe was unimaginably hot, dense, and expanding at a furious rate. Black holes can survive the evaporation of the universe's stars. Long after the last star has burned out, the universe will continue to expand and cool, eventually entering what cosmologists call the black hole era. During this epoch, which will last from around 10 to the 40th power to years after the Big Bang to 10 to the 100 power years, black holes will be among the only significant objects remaining. Stellar mass black holes will slowly evaporate through Hawking radiation, but supermassive black holes will take incomprehensibly longer to disappear. A black hole with 1 billion solar masses would require more than 10 to the 100 power years to evaporate completely, a timescale so vast that it makes the current age of the universe, a mere 13.8 billion years, seem like the blink of an eye. During this era, the universe will be dark, cold, and nearly empty, illuminated only by the faint glow of Hawking radiation from the slowly evaporating black holes. Eventually, even these will disappear, leaving behind only a thin sea of particles and radiation in an ever-expanding, ever-cooling cosmos. The far future of the universe, if current cosmological models are correct, is a place of ultimate entropy, a heat death, where all structure has decayed and all energy has been diluted to near nothingness, a final fade into silence and stillness. Intermediate mass black holes are rare. For many years, astronomers observed a puzzling gap in the black hole mass distribution. Stellar mass black holes ranged from a few to several tens of solar masses, while supermassive black holes started at hundreds of thousands to millions of solar masses. The region in between, from roughly 100 to 100,000 solar masses, seemed mysteriously devoid of black holes. These intermediate mass black holes are thought to form through multiple mergers of stellar mass black holes in dense environments, like globular clusters, or possibly through the direct collapse of very massive stars or gas clouds in the early universe. Detecting them has proven difficult because they are neither common enough to stumble upon frequently nor massive enough to create the kinds of dramatic observational signatures that supermassive black holes produce. However, in recent years, gravitational wave detectors have begun to catch glimpses of possible intermediate mass black hole mergers, and observations of certain star clusters and dwarf galaxies have found kinematic evidence, suggesting the presence of these missing link black holes. Confirming their existence and understanding their formation mechanisms could provide crucial insights into how supermassive black holes grow to their enormous sizes, and whether black hole mergers in dense stellar environments are a common pathway for black hole growth. They represent a bridge between the stellar and the supergalactic, a connection between the fates of individual stars and the evolution of entire galactic centers. Magnetic fields can shape black hole environments. The regions around black holes, particularly the accretion disks and jets, are threaded with powerful magnetic fields that play crucial roles in channeling matter and launching high-energy outflows. As gas spirals into a black hole, it drags magnetic field lines along with it, twisting and amplifying them through a dynamo process. These magnetic fields can store enormous amounts of energy and angular momentum, and when they become sufficiently strong or tangled, they can suddenly release that energy in flares or reorganize in ways that affect the rate of accretion. The magnetic fields also provide a mechanism for extracting rotational energy from spinning black holes, a process described by the Blandford-Znajek mechanism, where magnetic field lines anchored in the accretion disk and threading through the ergosphere of a spinning black hole can act like a giant generator, converting rotational energy into electromagnetic energy that powers jets. Recent observations with the Event Horizon Telescope have revealed that the magnetic fields near the supermassive black holes at the centers of the Milky Way and M87 are well organized and strong, consistent with the conditions needed to launch jets. Understanding the role of magnetic fields in black hole, accretion, and jet formation is a major frontier in astrophysics, requiring sophisticated simulations that combine general relativity with magnetohydrodynamics to model the complex interplay of gravity, magnetic forces, and plasma physics in these extreme environments. Some black holes have unusual spins. Most black holes spin in the same general direction as the matter that fell into them, but in certain cases, a black hole can end up spinning in a direction opposite to its orbital motion around a companion, an effect called negative or retrograde spin. This can happen through complex interactions in binary systems, or through accretion of matter arriving from different directions at different times, effectively reversing the black hole's spin over long periods. Gravitational wave detections have found evidence for black holes with high spins, including some spinning at close to the maximum rate allowed by physics, which is about 98% of the speed of light at the equator. These fast rotators likely acquired their spins through aligned accretion, where matter fell into the black hole consistently from the same direction, building up angular momentum efficiently. In contrast, black holes with low spins may have formed from stars with lower angular momentum or accreted matter from multiple directions, with different contributions cancelling each other out. Measuring black hole spins is challenging, but provides valuable information about their formation history and the environments in which they grew, offering clues to the processes that shape them over cosmic time. Black holes may not be the final state of matter. Some theoretical physicists have proposed alternatives to black holes as traditionally understood, suggesting that quantum effects near the event horizon might prevent the formation of a true singularity or even an event horizon itself. These hypothetical objects, sometimes called fuzzballs, gravastars, or other exotic names, would appear almost identical to black holes from the outside, but would have different internal structures that avoid the problematic infinities associated with singularities. In some models, the event horizon is replaced by a quantum surface with finite entropy, or the interior is filled with exotic forms of matter or energy that prevent complete gravitational collapse. While these ideas remain speculative and lack observational evidence, they represent attempts to reconcile quantum mechanics with general relativity and to avoid the conceptual difficulties posed by singularities and information loss. Testing these alternatives is extremely difficult because they make predictions that differ from classical black holes only in very subtle ways, or in regimes that are currently inaccessible to observation. However, as gravitational wave astronomy and other observational techniques become more sensitive, it may eventually become possible to detect signatures that could distinguish between classical black holes and quantum alternatives, providing a window into the quantum nature of gravity. Black holes can form from gas clouds. While most stellar mass black holes form from the collapse of massive stars, and supermassive black holes likely grow through accretion and mergers, there is a theoretical pathway for black holes to form directly from the collapse of gas clouds without ever passing through a stellar phase. This process, known as direct collapse, could occur in the early universe under special conditions where a gas cloud is massive enough and hot enough to remain supported against collapse by thermal pressure and rotation, but then suddenly loses that support and collapses catastrophically. The resulting black hole could have a mass of thousands or tens of thousands of suns, providing a possible seed for the growth of supermassive black holes in young galaxies. For direct collapse to work, the gas must remain primarily atomic hydrogen, unable to cool efficiently by forming molecular hydrogen, which would fragment the cloud into smaller clumps that form stars instead of a single massive black hole. This requires the gas to be bathed in a strong ultraviolet radiation field that dissociates any molecular hydrogen that tries to form. Such conditions might have existed in pockets of the early universe, particularly near the first generation of stars or quasars, making direct collapse a possible, though still unconfirmed, pathway for black hole formation in the cosmos's first billion years. There are more black holes than we can see. The vast majority of black holes in the universe are invisible to us. Stellar mass black holes, unless they are actively accreting matter or have a companion star, emit no light and are nearly impossible to detect. Estimates, based on stellar evolution models, suggest that our Milky Way galaxy alone may harbor 100 million stellar mass black holes, but only a few dozen have been confirmed through observations. Most of these detected examples are in binary systems, where their gravitational influence on a companion star or the X-rays from accreting gas reveal their presence. Isolated black holes, drifting through space, are essentially invisible unless they happen to pass in front of a background star, causing a brief gravitational lensing event that lasts weeks to months as the black hole's gravity magnifies the star's light. Surveys designed to detect such microlensing events have identified a few candidate isolated black holes, but confirming them and measuring their properties is challenging. As observational techniques improve, particularly with gravitational wave detectors and next-generation telescopes, the census of black holes will grow, revealing a hidden population that outnumbers the visible stars and providing a more complete picture of these dark remnants scattered throughout the galaxy. Black holes challenge our understanding of reality. At the boundary between the known and the unknowable, black holes force us to confront the limits of physics and the nature of reality itself. They sit at the intersection of the two great pillars of 20th century physics, general relativity and quantum mechanics. Two theories that are individually spectacularly successful, but seem fundamentally incompatible at the extreme conditions found near singularities. Resolving this tension requires a theory of quantum gravity, which might reveal that space-time itself is not fundamental, but emerges from something deeper, perhaps a web of quantum entanglement or a discrete structure that only appears continuous at large scales. Black holes also raise questions about the nature of information, causality, and the arrow of time. Do physical laws break down at singularities, or do they remain valid in a form we do not yet understand? Is space-time smooth all the way down, or does it become grainy at the Planck scale? Can information escape from a black hole through subtle quantum effects, or is it truly lost? These questions push at the boundaries of human knowledge, driving physicists to develop new mathematical tools, conduct ever more precise observations, and think creatively about the fundamental structure of the cosmos. Black holes are not just astronomical objects, but natural laboratories where the universe tests its own deepest principles, offering us glimpses into realms where our current theories falter and new physics awaits discovery. Second-generation black holes are created by mergers. When two stellar mass black holes merge, they create a new black hole with a mass equal to the sum of the original two minus the energy radiated away as gravitational waves. This second-generation black hole can then participate in subsequent mergers, creating even more massive black holes in a kind of hierarchical growth process. Recent gravitational wave detections have found evidence for such second-generation black holes, identified by their unusually high masses or spins that suggest they formed from earlier mergers rather than directly from stellar collapse. One such event, detected in late 2024, involved black holes with masses and spins that indicated they were likely the products of previous mergers, born in dense stellar environments where multiple black holes could interact and merge over time. These findings support the idea that black hole mergers are not isolated events, but part of a larger evolutionary process that can build black holes up to intermediate masses through repeated coalescence. In globular clusters, where thousands or millions of stars are packed tightly together, this process may be particularly efficient, creating a population of intermediate mass black holes through a cascade of mergers. Understanding second-generation black holes and their properties helps astronomers piece together the complex story of how black holes grow and evolve in different environments. Throughout cosmic history, black holes can be found through their lensing effects. Even an isolated black hole, far from any stars or gas, can betray its presence through gravitational lensing. As a black hole passes between Earth and a more distant star, its gravity bends the light from that star, causing it to brighten and creating multiple distorted images. The duration and characteristics of this microlensing event depend on the black hole's mass, distance, and velocity. For a stellar mass black hole, the brightening typically lasts weeks to months, and careful analysis of the light curve, the pattern of brightening and fading, can reveal the lens's mass. If the lensing is observed in multiple wavelengths, astronomers can sometimes detect an additional signature called astrometric microlensing, where the apparent position of the background star shifts slightly due to the light bending, providing even more information about the lensing object. Several surveys monitor millions of stars looking for these rare events, and a few candidates for isolated black hole lenses have been identified, though confirmation remains challenging because other objects, such as neutron stars or dim white dwarfs, can produce similar signatures. As monitoring campaigns become more sophisticated and space-based telescopes provide higher resolution observations, gravitational lensing may become one of the primary tools for finding and studying the galaxy's population of isolated black holes. Black holes can have electric charge, but usually don't. In principle, a black hole can carry electric charge, and solutions to Einstein's equations describe such charged black holes, known as Reissner-Nordström black holes. These solutions have properties quite different from uncharged black holes, including two event horizons and, in the most extreme cases, naked singularities that are not hidden behind horizons. However, in practice, astrophysical black holes are expected to be nearly electrically neutral. Any significant charge would quickly be neutralized by attracting oppositely charged particles from the surrounding environment. The electromagnetic force is vastly stronger than gravity, so even a tiny net charge would create electric fields strong enough to pull in ions and electrons until the black hole's charge balanced out. Additionally, the matter that forms black holes, whether from collapsing stars or accreted gas, is generally neutral or contains equal amounts of positive and negative charges, leaving no net charge to be inherited by the black hole. For these reasons, astronomers usually treat black holes as uncharged when modeling them. The theoretical charged solutions remain important for understanding the full range of possible black hole geometries and for exploring the mathematical structure of general relativity. But in the real universe, black holes are essentially characterized by just their mass and spin. Black holes may contain baby universes. A speculative idea in theoretical physics is that the interior of a black hole might connect to a separate, causally disconnected region of space-time, effectively a baby universe branching off from our own. In this scenario, the matter that falls into the black hole does not reach a singularity, but instead continues into an expanding region with its own space-time, isolated from the parent universe. From the outside, this new universe would be invisible, hidden behind the event horizon, while observers within it would see an expanding cosmos around them, unaware of the black hole's exterior. This concept arises from certain solutions to the equations of general relativity and has been explored in the context of cosmology and quantum gravity. If such baby universes exist, they could provide a way for the universe to continually reproduce, with each black hole potentially spawning a new cosmos with its own physical laws or constants, slightly varied from the parent. While this idea remains highly speculative and lacks any observational support, it illustrates the profound strangeness of black holes and the possibilities that arise when we take general relativity seriously in extreme conditions. It also raises deep philosophical questions about the nature of existence, causality, and the structure of the multiverse, challenging us to think beyond the boundaries of the observable universe. Black holes influence galaxy evolution. The relationship between supermassive black holes and their host galaxies is one of the most important and surprising discoveries in modern astrophysics. Observations have revealed that the mass of a galaxy's central black hole is tightly correlated with the properties of the galactic bulge, the dense spheroidal region of stars surrounding the center. This suggests that black holes and galaxies do not evolve independently, but influence each other's growth through feedback processes. When a supermassive black hole accretes matter rapidly, it can release enormous amounts of energy through radiation and jets, heating the surrounding gas to temperatures that prevent it from cooling, fragmenting, and forming new stars. This feedback can effectively shut down star formation in the galaxy, regulating its growth and possibly explaining why many massive galaxies are no longer actively forming stars today. Conversely, starbursts and galaxy mergers can funnel gas toward the central black hole, triggering episodes of rapid accretion and growth. This co-evolution of black holes and galaxies has profound implications for understanding the universe's large-scale structure and the diversity of galaxy types observed across cosmic history. It suggests that black holes, despite their small size relative to galaxies, play an outsized role in shaping the cosmos. The shadow of a black hole is larger than its event horizon. When the Event Horizon Telescope captured the first image of a black hole, the dark region visible in the picture, called the shadow, was about 2.5 times larger than the black hole's event horizon. This is because the black hole's gravity bends light from behind it, creating a dark region that includes both the event horizon itself and an area around it where light is captured after being bent into the black hole. The boundary of the shadow corresponds to the photon sphere, the region where light can orbit the black hole in unstable circular paths. Photons emitted just inside this radius spiral into the black hole, while those just outside can escape, though they are significantly redshifted and delayed. The size of the shadow depends on the black hole's mass and spin, with faster spins creating slightly smaller and asymmetric shadows due to frame-dragging effects that make one side appear brighter or larger than the other. Measuring the shadow's size and shape allows astronomers to test general relativity in strong gravitational fields and to determine the black hole's properties with precision previously impossible. Future observations with higher resolution may reveal even finer details, such as the photon ring, a nested series of bright rings created by light orbiting the black hole multiple times before escaping. Black holes eventually disappear. According to Hawking's theory, black holes are not eternal. They slowly evaporate through the emission of Hawking radiation, losing mass over time until they finally vanish in a final burst of energy. For stellar mass black holes, this process takes an unimaginably long time, on the order of 10 to the 67th power years, for a black hole 10 times the mass of the Sun. Supermassive black holes take even longer, with evaporation times that dwarf the current age of the universe by factors of 10 to the 100 power or more. As a black hole loses mass, it shrinks and its temperature increases, causing it to radiate more quickly in a runaway process. In the final moments, when the black hole has shrunk to a tiny fraction of its original size, it would glow white-hot, emitting a tremendous burst of gamma rays and particles before disappearing entirely. What, if anything, remains after this final evaporation is a matter of debate. Some theories suggest that a remnant, a stable quantum object with finite mass and size, might be left behind, while others predict that the black hole disappears completely, leaving only the radiation it emitted. This final fate of black holes, playing out over timescales that make even the age of stars seem fleeting, represents one of the ultimate endpoints of matter in the universe, a slow fade into light and energy, a return to the quantum foam from which all things may have emerged. Falling into a black hole would be a one-way journey. Once you cross the event horizon of a black hole, there is no possibility of escape, no matter how powerful your engines or how clever your strategy. The structure of space-time inside the horizon is such that all paths lead inexorably toward the singularity. In a very real sense, forward in time, inside a black hole, means closer to the singularity, just as outside the horizon, forward in time means later. The singularity is not a place you can avoid by moving sideways or turning around. It is in your future, as inevitable as tomorrow. From your perspective as you fall, time would continue to pass normally, and you might not notice anything unusual at the moment you cross the horizon, especially for a supermassive black hole where tidal forces are weak at the boundary. But you would have only a finite amount of proper time left before reaching the singularity, a time measured in fractions of a second for stellar mass black holes or hours for the most massive supermassive examples. During this brief interval, you would experience increasing tidal forces, be stretched and compressed, and ultimately torn apart at the quantum level as you approach the singularity where curvature becomes infinite. For observers outside, watching you fall, you would appear to slow down asymptotically as you approach the horizon, your image freezing and fading, never quite crossing over from their point of view. This asymmetry in perspectives illustrates the profound strangeness of time and causality near black holes, where your fate and the outside universe's perception of it diverge dramatically at the boundary between the escapable and the inescapable. And now, the stars begin to dim behind your thoughts. We have drifted together through the deepest enigmas of the cosmos, from the gentle warping of space around distant giants to the violent births of stellar remnants, from the slow evaporation of microscopic black holes to the eternal patience of supermassive anchors at galactic hearts. You have wandered through event horizons and photon spheres, danced along gravitational waves, and gazed into shadows cast by objects that let nothing escape. You are a part of this universe, not separate from its mysteries, but woven into its fabric. The atoms in your body carry the memory of stars, and the forces that shape galaxies also guide the rhythm of your breath. The black holes we have explored tonight are not distant abstractions but integral parts of the cosmic story, participants in the long, slow evolution of structure, energy, and time. Tonight, as you rest, the universe continues its work. Black holes merge in distant corners, light bends around invisible masses, and space-time ripples with the echoes of ancient collisions. And somewhere in the gentle turning of galaxies, in the patient spiral of matter toward darkness, in the quiet evaporation that takes longer than thought can hold, the cosmos unfolds in ways both beautiful and strange. You have done enough for today. Close your eyes, rest, and dream of other skies, of horizons that curve away into mystery, of light that bends and time that slows. The universe will keep turning without you for a while. Let your breathing slow. Let your mind loosen its grip on the day. Float free like a particle near the photon sphere, hovering between worlds, suspended in the gentle dark. The black holes will still be there when you wake, patient and eternal, holding their secrets close. But for now, you can let go, drift into stillness, slip into the quiet night, and rest in the knowledge that even in darkness, there is wonder, and even in mystery, there is peace. Good night.